Last day, we started talking about a really important concept, this notion of fields. In particular, we said that any object with mass in outer space sends out, like the invisible tentacles of an octopus, a gravitational field, and that's how it's able to reach out and snare something in its gravity well. It's not action at a distance, it is touching the other object, it's just touching it invisibly with something you can't see or touch, but you can certainly detect it. We said any objects with charge send out an electric field. And we noticed the equations and the concepts for electric field really resembled the same concepts for gravitational field. And the reason is we're now looking at the field mathematics of physics, and they will overlap quite a bit. We said you can calculate the gravitational field in two ways. The first way you can calculate it is if you know what's causing it. In the same way, the first way you can calculate gravitational field is if you know how big the planet is. So planet, we have mass, charge. Electric field, we have charge. KQ over R squared. Then we said you can also calculate it if you don't know what's causing the gravitational field, but you're in space somewhere, and Kayla, you suddenly detect an electrical force. You can calculate how big a field you're stuck in by measuring the electrical force, dividing it by the charge. By the way, this also gives you another equation for electrical force. How would I get the letter F, the F by itself? So another consequence of this is that electrical force is equal to the charge at that location times the field at that location. Humbly, I'll suggest this is the electric equivalent of gravity equals mg, which was our shortcut on the Earth. They parallel each other very, very similarly. That's handy as well because sometimes you'll know the electrical field and you'll know both charges. Instead of going K, Q1, Q2 over R squared, hey, if you know the electrical field, multiply it by the charge of that location, and you got the force right there. A little shortcut. Okay? We said the units for electrical field were newtons per coulomb. Pops out of this equation here. Much like gravitational field was newtons per kilogram or meters per second squared, there is going to be another set of units coming down the road in a couple of lessons, but not just yet. We said that we don't put the negative or positive in. Instead, we have to define the direction, and we're going to define the direction of an electric field by saying, which way would a positive charge sitting at that location want to travel if it could? A tiny positive test charge. James, how tiny? So tiny it doesn't have its own electric field, because if it had its own electric field, that would change the question, as some of you who are doing the bonus video game discovered. As soon as you add another, one of the reasons the bonus video game is tough is this, as soon as you add another charge somewhere, the original charge moves differently from the very beginning. It goes over the whole page. We did also show you the most addictive bonus video game. Riley, you'll have to read the notes, and I'll put it up on the website as well. We said that you can represent electric fields with lines, electric field lines. The arrows tell you the direction of the electric field, which means if it's a positive charge causing the electric field, arrows will always point away. If it's a negative charge causing the electric field, arrows will always be pointing towards. A great multiple choice question that you'll see time and time again is I'll give you a picture of an electric field, but I won't label which charges are which, and a multiple choice question would be which charges are positive, which charges are negative, and I'll give you a bunch of different ones to pick from. You'll see that in your big package quite a bit. This is the electric field pattern. Well, you know what? These are terrible. These are hand-drawn here. Here's the electric field between two like charges, and this was drawn with a computer, a little bit better. Here's the electric field between two unlike charges, and I'm going to argue for both of these. I actually don't do this yourselves, but Drake, I wouldn't need to give you the polarity of the charges. You could figure it out, and this would be a nice multiple choice question. If I called that charge A and charge B, the multiple choice question would say A positive, B positive, A negative, B negative, A positive, B negative, A negative, B positive. I think that's all the four possibilities right there. There's a great multiple choice little question, okay? Michael Faraday was the one who gave us a lot of our electricity physics. Michael Faraday, great story. I got to pause the video and go on a little bit of a rant here. So I've gone on my little Faraday rant. So the idea of electric field originated with Michael Faraday. 1791 to 1867. I think I said 1850s, probably closer to 1810 was when he started working for Humphrey Davy. But he used a different way of representing field. He used lines of force. He used pictures. He was not a math guy. Okay? So here's a picture of the electric field from a positive charge, picture of electric field from a negative charge. These two charges would be the same magnitude. Why? Because they have the same number of lines. As you move further from a charge, what happens to the strength of the electric field? It gets weaker. As you move further away, what happens to the distance between the lines? They get bigger. So Faraday said the distance between the lines reflects how strong the electric field is at that location. That works quite well, actually. It's kind of nice. So, for example, in this picture, the field is getting weaker and weaker as I move this way. The field right here is getting stronger because the lines are converging closer together. Summary. This is where we left off. Electric field can be found using the definition if we're told the force on a test charge. So the same way that G is found by hanging a mass and measuring the force that it experiences. Electric field can be found if you know the electric force at a location and the charge at that location. This is the one that's on your formula sheet. I think it's the second equation you have. It can also be found using the point charge equation, really using Coulomb's law. If we are told the charge that's creating the field in the first place, we can say electric field is equal to K big Q over R squared. Recall, electric field is found by considering a positive test charge. I always ask, which way would a positive want to move if it could? The shorter version of that, Brandon, is it's always Brandon, away from a positive towards a negative. The only reason I don't use that one is sometimes in your picture you won't have both charges and it can be confusing. So I always fall back on, well, which way would a positive sitting there want to move if it could? That works if I only have one charge, I can still figure it out. The force on a charge can be found by using Coulomb's law. Although instead of writing it that way, look up, I'll write it the way we wrote gravity. Big Q, little q over R squared. Big charge causing the force, the electric field. Little tiny asteroid charge stuck in the electric field. And you can also find it by getting the letter F by itself in this equation. So the electric force can also be calculated by QE. And remember I said that was very similar, Robbie, to mg that we used to use in Physics 11. Recall, direction of electric force is figured out by using like, unlike. Okay? Oh, and since both force and fields are vectors, we'll have to add them vectorially. If they're in a nice straight line, we can go winner minus loser. Woohoo! If they're not, tip to tail time. Okay? I already stuck the homework at you. I just wanted to talk a little bit about number 10. So number 10 is very similar to the electric field toy that I brought out last day that I was playing around with at the beginning of class today. So for number 10, really, we can use this. Let me erase this here. I think what you have as a free body diagram is gravity pulling an object down. I notice it's 125 grams, so that's 0.125 kilograms. The electric field is upwards. The charge is positive. So which way would a positive want to move if it could if the electric field is upwards? Upwards, don't overcomplicate it, right? Positive charges move in the direction of an electric field because the electric field is defined as which way a positive would want to move if it could. So there is an electric force, sorry, not E, Mr. Dewick, there's an electric force up. I don't know which one is bigger and which one is smaller. It says find the net force on the particle. I'd have to crunch these ahead of time. One of these is probably winning. And the reason I suspect one of these is winning is part B asks me to find the speed. You know what? I'm going to find the acceleration. And then I'll VI is 0, find VF, T is 2.5. So there's a nice little review of a good free body diagram. I just don't know which one of those two is winning. I'd have to crunch them ahead of time. Okay? So that's a little bit about the homework from last day, and now we move on to today's lesson. Another lesson? Yep. So lesson 4, hey, last day was lesson 2. I skipped lesson 3. Actually, I combined lessons 1, 2, and 3 into 2 lessons. I was going to say 2 easy lessons, 2 nerdy, cool, interesting, conceptual lessons. We're going to talk about electric potential energy, and for electric potential energy, we have the same problem as cosmic gravitational energy. The force is not constant as soon as you move away. The force is changing, which means it's going to look really, really similar. You may want your formula sheet visible just so you can see where this puts together, how this comes together. I said this. We define electric potential energy. I'm going to use PE, and the reason I'm going to use PE is I'm going to use a capital E for electric field. I'm going to use PE for potential energy. Now, on your formula sheet, Robbie, they use this for potential energy, and to me, that has potential, no pun intended, to get confusing, an E and an E. So I avoid doing that. That's just a Dweck quirk. I don't think you'll see another. By the way, the proper symbol, part of the problem is this is not the symbol, this is not the letter to use for energy. The proper letter you're supposed to use for energy is a capital U. Why U? Because not all physics was done by English-speaking people. Anyways, if you take university physics, probably that will become your go-to symbol for kinetic energy would be UK, potential energy would be UP, and any other forms of energy that you'll use the letter U. So we say that electric potential energy reflects the work that must be done to move a negative charge. Let's all of us put a little negative on Q right there. From a positive charge, let's put a positive next to the capital Q right there, out to infinity. Does that little negative charge Q want to move out to infinity? No, it wants to fall, and I'm going to use gravitational terms, it wants to fall down to the earth. It wants to fall down to the positive charge. So for us to move it out to infinity, and by out to infinity, I mean so that it has no potential energy, so that potential energy is 0, so that it's completely out of the electric field of this object, we would have to do work because it would be resisting us the entire way. Or, if the charges are like charges, how much work it would take if this was a positive to start here and push it all the way in, because now it doesn't want to fall. It actually wants to repel, so now you would have to do work to push it in. But no matter what, you would have to apply some energy. You would have to do some work. You'd be pushing and pushing and pushing to bring it in. Or you'd be lifting and lifting and lifting to pull it out. Recall, the force between two charges is not constant and varies with distance. Again, this was supposed to say F equals K Q Q over R squared. I don't know why the little thing went wonky like that. And again, Kayla, we can't use force times distance because the force is changing. Instead, we're going to have to find the area under a graph using calculus. You know what? I'm just going to walk you to the same punchline that we did for cosmic potential energy. Potential energy for electricity. Well, how was the cosmic potential energy for gravity related to the force? It was identical, but no R squared, just an R. Right? It's going to be the same thing. K, Q1, Q2 over R. Now, Mr. Dweck, that's not quite right. When we did potential energy for gravity, we had a negative in front. Yeah, we did. But that's because for gravity, things always fell down. For electricity, can things want to fall up? Yeah, because like charges repel. So we're not going to put a negative in front of the equation. Instead, we're going to include the positive and negative signs in the equation itself. And that will take care of whether I needed or have a negative or a positive potential energy at that location. Energy, scalar or vector? Energy, scalar or vector? Scalar, yes. And so if you're looking for a dumb thing, scalars include signs. Ready? If you're looking at your formula sheet at the electrostatic section, which maybe some of you could right now, Here's what I always told my students. See the first line? The three equations on the first line under electrostatics? Listen close. Forces and fields, first line, forget the signs. We don't put negatives and positives in. That's why I had you put absolute value signs around them. Scalar signs. So right beneath that on the second line, I think that's where you have the potential energy equation. You're going to put positives and negatives in. Otherwise, Nevada, it's the same thing. K, 9 times 10 to the 9th, the same way big G was 6.67 times 10 to the negative 11. Plug in the charges, the same way you plugged in the masses. Only thing is, the numbers will typically be nicer. Oh, by this relationship, the potential energy is 0 out of infinity. If you take the limit as r approaches infinity, for those of you in calculus, you'll get 0. By this relationship, unlike charges, will have negative potential energy, which makes sense because to get it out to 0, you have to add energy. They don't want to move out to 0. They want to be attracted towards each other. And by this relationship, like charges, have positive potential energy. That's because when they head out to infinity, when they fall out to infinity, they'll be losing energy. They have to lose energy to get to 0. That's very profound if you stop and wrap your brain around it for a while. It all works. Example 1. Let's do something with some numbers. Find the potential energy of a negative 75 microcoulomb charge that's 3 centimeters, haha, nice try, 0.03 meters, from a positive 120 microcoulomb charge. That's part A. This picture right here is what we're talking about. We're going to assume this bigger charge is like thumbtacked in place or glued to the paper or something is holding it. Which way does this charge here want to fall or move? Away or towards? Towards. So part B says write a work energy equation if I move it out to infinity. If I want to move it out to infinity, I am going to have to do work because it doesn't want to move that way. And then C says, find the work done by that applied force. What applied force? Let's imagine there's a little invisible angel or something that's just pulling this thing to the right, heaving it away. Little elves, little leprechauns, whatever. Something that's not in the picture. Okay? A says, find the potential energy. Well, that's going to be K Q1 Q2 over R. Not R squared. See it there, Drake? Yep. K, a nice constant, 9 times 10 to the 9th. Charge 1 is a positive, and I'm going to put the plus sign just to remind you that I did look at the signs. 120 microcoulombs times 10 to the negative 6. Charge 2, negative 75 times 10 to the negative 6 microcoulombs. Divided by 0.03. By the way, what if I wanted to find the force between them? Square the bottom and chuck the negative. So that's also an easy backspace edit if you have a calculator that lets you do that and it wants both. How many joules of force do we have here? You know, I think this will actually work out evenly. Sorry, how many joules of energy? I said joules of force, didn't I? How many joules of energy do we have here? 9 times 10 to the 9th, 120 microcoulombs, negative 75 microcoulombs divided by 0.03. Do you get negative 2,700 joules of energy? Double check me. Yeah? Negative 2,700 joules. Direction. Direction. It's a scalar. It's a trick question. No direction, right? Speaking of no direction. So far, so good? James, what does part B want me to do?
Write a work energy equation.
For this, hopefully you've clued in that we're rarely using force times distance. We're using our universal work is the change in potential plus the change in kinetic. And honestly, if you stop there, I would say, yeah, that's the equation. James, does this question suggest before or after that there's any speed of this particle?
Yeah.
It suggests there's a speed. Look at the picture. Are you guessing?
Yeah.
Okay. James, look up, my friend.
Yeah.
See this right here? Do you see a V, a speed anywhere there? See this right here? Do you see a speed or anything right there? If you read the question, does it suggest that it's moving at all? I think we're moving it ourselves, starting at rest, ending at rest. You okay with that? What does that mean, James, my friend? We can do this. Not always, but this time we can. James, I've changed the potential. What's changing anything? Good. Okay. I would take that. Andy, what's part C want me to find?
The work done by the apply.
Oh, it actually wants me to solve this work energy equation. Okay, I can do that. What's my final potential energy if I end up out at infinity? 0 minus. What was my initial potential energy? We calculated that, Andy, in part A.
Negative 2,000.
You notice, Andy, I get a minus minus, which is a, and that's good because I would have to add energy to this to get it there. It doesn't want to go there on its own. I have to add energy. So as I said, as long as you take care of the signs, all the physics itself will make sense in the end, Sinead. It'll look a little murky in the middle, but yeah, I end up with, it would take 2,700 joules of energy to move this charge out to infinity, and really, in real life, to move this charge a long ways away. Close enough to infinity that the electric field is basically 0. Okay. Turn the page. So by this equation, this means, Connor, that like charges have positive potential energy. And I'm going to argue, Nick, this makes sense because it takes work to overcome the repulsive forces to push them together. So here's a question, example 2. Find the work required for an external agent, leprechaun, invisible angel, whatever you want, little elf, to place a positive 2.5, careful, millicoulomb charge. I'll have to look up what milli is. I think it's 10 to the negative 3, but I'll check. 5 meters away from a positive 1.75 millicoulomb charge. Oh, hey, I was nice enough to even include it there. And we're going to assume that we're initially an infinite distance away. Okay. Drake, what does this question want me to find? The work. So instead of walking through part A, B, and C like I did in the previous question, we're just going to jump to the whole schmear. I'm going to say, well, work is the change in potential plus the change in kinetic. Drake, if you read this question, if you look at the picture, does it look like we're starting out at rest and ending at rest?
Say yes.
Yeah.
So what's our change in kinetic energy if there's no change in speed? So we can cross that out. I won't do that all the time. Sometimes I will also say, and we want to be traveling at such a speed. Okay. Drake, what's changing anything? So this is going to be PE final minus PE initial. Drake, do you remember how much energy do we have out at infinity? It's a nice number. This is how we've defined it, 0. So look at the picture. Is infinity our final location or our initial location? Which of these can I cross out is what I'm really wondering. Oh, so you're telling me I can do this? Nice. Now we're doing potential energy. What kind of potential energy? Not gravitational. This is electric potential energy. So I'm going to use our new equation. It's going to be K Q1 Q2 over R. And we are going to include the signs. Scalars, signs. Let's finish this together, you and I, Drake. What was K? That's that constant. Yeah. Probably the nicest constant we'll use all year compared to, well, there's other conversion factors that we bring out as well, and this is the nice one. By the way, I think it's actually 8.998 or 8.9998 times 10 to the 9. Close enough. Q1, that'll be the fixed charge, positive 1.75, and it's milli, which is 10 to the negative 3, or you can just multiply by 0.001. Q2, the moving charge, positive 2.5 times 10 to the negative 3 millicoulombs. Divided by, Drake, what's our final distance? What's our final R?
5.
Yeah. You know what? I think this will work out nicely too, yeah? 9 times 10 to the 9th. 1.75 times 10 to the negative 3. 2.5 times 10 to the negative 3 millicoulombs. I'm expecting actually a fairly big energy here. Although 5 meters, we're not getting very close. Remember last question, we got 3 centimeters away. The closer you get, the stronger the force, right? You get 7875? I'll go 7880. And that's joules. So one way to look at this, Sarah, is we do work trying to bring 2 like charges together. We do work trying to split 2 unlike charges apart. We can also start to model the same physics as dropping an object. When I drop an object, it speeds up. It's exchanging potential energy for what kind of energy? Kinetic. We can bring in the law of conservation of energy, G. For energy, a scalar, we're going to include the positive or the negative in the equation, but forces and fields will decide the direction ahead of time by looking at the polarity. We won't actually put the pluses and minuses in the equation. If there is no external agent pushing the charges around, like we had invisible leprechauns here, then energy will be conserved. The amount of energy you had at the beginning must be the amount of energy you had at the end. Nothing's doing work. Okay. An electron is originally 2.5 times 10 to the negative 11 meters, really close, to a proton, and at rest. I'd probably underline the word at rest. It's released, and it moves directly towards the proton. Nick, that makes sense. The electron would want to move towards the proton. Find its speed when it is that far from the proton. Nick, what's this question asking me to find? Okay. Nick, in your mind, if you turn your head sideways, you don't need to, but if you kind of turn your head sideways, if we pretend that the height goes in that direction, the same as when I drop something, height is vertical, I would say to you, is there a change in height? Is there going to be a change in speed? I think so. Is there a yucky curvy force? There is. You know what this is a job for? Conservation of energy. So let's start out by going KE initial plus PE initial, KE final, plus PE final. Hey Nick, are any of these 0? Let's first of all look at our kinetics. Are any of our kinetics 0? Are any of our potentials 0? Well, the only way we'd be 0 is if we were out at infinity sometime, and I don't think we're ever out at infinity, so be nice. Okay. I think I'm trying to get the V inside there by itself. So Nick, I'm going to move this over to this side. That's going to give me initial minus final. I'll be very careful with that. Equals a half mv final squared. Am I going to use mgh? No. This is not gravitational potential energy. This is electric potential energy. So it's going to be K Q1 Q2 over, and I'll be very careful with my numbers, our initial goes there, which I think is going to be the bigger value, minus K Q1 Q2 over our final. That equals 0.5 mv final squared. I could, I guess, divide everything by 0.5 m and square root. I'm not gonna. Nick, I'm gonna actually crunch this and just get an answer. First of all, let's substitute our values in. Did I leave you the whole page? I hope I did. Good. Nick, what was K? 9 times 10 to the 9th, yes? Okay. It's a printer, Nick. Relax. Squirrel, back here now. Okay. You good so far, Nick? What's charge 1? Are you ready? It's a proton! He's positive or negative, because we have to include signs now. Okay, I'll put the plus just to remind myself I checked. 1.6 times 10 to the negative 19. Charge 2, it's an electron.
2.5 times 10, negative 2.5 times 10.
It's an electron. Help them out, folks. You kidding me? Yes, negative 1.6 times 10, negative 1. That's the charge on both a proton and an electron. It's why we call it the elementary charge. Divided by, Nick, you rattled off some number that I think had meters next to it that couldn't possibly be a charge. Nick, what's the initial radius? Please read very carefully.
2.5 times 10 to the negative 12.
Minus, hey Nick, ditto mark times ditto mark times ditto mark divided by. By the way, folks, you've got to be able to handle that. You're going to be doing a lot of physics with electrons and protons. I've given you their charge. I've given you their masses. What's the final distance, Nick?
4 times 10 to the negative 12.
And that's going to be 0.5 mv squared. Okay. You know what? I may type this. Yeah, I'm going to try typing this in one fell swoop, the whole thing. 9 times 10 to the 9th, 1.6 times 10 to the negative 19 times negative 1.6 times 10 to the negative 19 divided by, you know what? I won't. I'll do it in steps so that in my notes you can see what we did. I was going to do it all in one fell swoop. The first one, I get negative 9.216 times 10 to negative 18. Anybody double check me? Yep. Okay. What did I say? Negative 9.216. Negative 9.216 times 10 to the negative 18. Now, I'd be a bit nervous right now because right now, with that negative, I might end up with a negative speed, which doesn't make sense at all. But let's see. Minus. Now, Drake, I'm going to backspace and edit, and all I need to change is the 2.5 to a 1.0. And I get negative 2.3104 times 10 to negative 17. Sorry, negative 2.304. I think it's like a 1 in there. Negative 2.304 times 10 to the negative 17. That equals a half mv squared. Hey, Nick, do you notice the minus minus? Which is a? Okay. So I'm going to multiply this by negative 1, and now it's a positive. And then I guess I'm going to add to it negative 9.216 times 10 to the negative 18. I'll add those together. And I get a positive answer. Whew. I'll write down that whole thing. It's not too many sig figs. 1.3824 times 10 to the negative 17. 1.3824 times 10 to the negative 17 equals 0.5 mv squared. Nick, how would I get the v by itself? Okay, I'm going to do that on this line. I'm going to go divide by 0.5 m. That gives me a v squared. That gives me a v squared. Oh, I didn't want to do that. Square root. Okay, so final answer. I'm going to get v equals the square root of 1.3824 times 10 to the negative 17 divided by 0.5 m. What's moving in this question? It's an electron. It's on your sheet somewhere, yes? 9.11 times 10 to the negative what? Okay. So I'm going to take this number and I'm going to divide it by 0.5 times 9.11 times 10 to the negative 31. Check. Square root. Quick like a bunny. And I get, it's moving pretty fast. Not faster than light, though, so at least my answer is within the bounds of the universe. And electrons have very little mass. A very small force will get them moving pretty fast. 5.51 times 10 to the 1, 2, 3, 4, 5, 6 meters per second. I like this question, I like this question, I like this question. There's going to be some question, almost certainly, involving conservation of energy, GG, but with our electric equation. Okay. Do you remember I said to you at the beginning of this unit, you know, a lot of the math is going to look really similar to gravity? A lot of the math is going to look really similar to gravity. Here's a nice question. How much potential energy does this charge possess? That one. You know what? Let's label these. Let's call, let's call the main one down here charge 1. We'll call this one up here charge 2. We'll call this one up here charge 3. So it really is asking how much energy does Q1 possess? This might look really ugly because do you see angles? Do you see angles? I don't, because energy is a scalar. I don't care where they put this. They could have put a really yucky angle. I don't care. They could have put this diagram any which way. I don't care. What do they want me to find? How much energy this has? Well, you know how much energy this has? I'm going to find the potential energy between charge 1 and charge 2. I'm going to find the potential energy between charge 1 and charge 3. Do I need to find the potential energy between charge 2 and charge 3? If they had asked for the total energy stored in this system, I would also then find that. I need to do some Pythagoras to find that distance. But they didn't ask for that. They just want the energy on this charge. And then I'm just going to add them up. But Robbie, they're scalars. I'm just going to add them up. Not vectorially, just add them up. So potential energy between charge 1, that's going to be K, Q1, Q2, over the distance between charge 1 and charge 2. 9 times 10 to the 9th. Charge 1, negative, and I'm going to include the sign because we're in scalarville, 1 microcoulomb. Positive 5 microcoulombs. Mr. Dewitt, do we need to put a plus sign in the equation? In your work, don't. I'm putting the positives in just to let you know when you're studying in your notes. We did put positives and negatives in. Divided by 0.02. 9 times 10 to the 9th. Negative 1 microcoulomb. Positive 5 microcoulomb divided by 0.02. Do you get negative 2.25 joules? Anybody else? Yep. Let's also then find the energy. Oh, that didn't work. Between charges 1 and charge 3. Can I go straight to numbers? I'm going to be daring and go straight to numbers. 9 times 10 to the 9th. Charge 1, negative 1 microcoulomb. Charge 3, negative 2 microcoulombs. Divided by 0.04. Oh, wait a minute, Mr. Dewick. Be clever. Just backspace and edit. Ha-ha. So it's going to be negative 2 and divided by 0.04. Do you get positive 0.45? So the potential energy at charge 1 is going to be negative 2.25 plus positive 0.45. I can probably do that in my head. Negative 1.8? Double check me, but I think so. Yeah? Negative 1.8 joules. This is the beauty, Sam, of energy. This is why whenever we had yucky diagrams, if we could use energy to solve it, scalar was always nicer. No tip to tail, no trig, no nothing. Now, if I had said find the net force on charge 1, yeah, got to do a bit more work. Okay. your pencils down, look up. What's your homework? Number 1, except you can cross out the third diagram. Number 2 is good. Number 3, if you look at it, what's number 3 asking you to find? Speed when it's allowed to move. This is going to be conservation of energy. This is like dropping an object, except Drake, like charges. So in this case, when you drop this, it falls up. Sorry, but it does. It repels. But it's going to be the same physics. It's a conservation of energy question. Okay, so number 3 is a nice one. I think 4 is good. Did I fix your diagram in number 5 so that underneath there it does say final instead of, yeah, okay. So 5 is good. I'm going to skip 6. 8 is good. So 8 is a nice test question, written question. If you're asking, what could I give you on a written test? Hey, how about 3 charges like that and say, find the net electric force on one of them and then find the net electric field at point X. For all of these, you're going to have to add them vectorially, but they're in a nice straight line, so instead of Tori going tip to tail, you can at least go winner minus loser. Okay? We're getting towards the end of the year. I'm tempted to give you, no, I won't worry about number 9 or number 10. They're good review. So that gives you some. And also, I suspect most of you haven't finished the electric field stuff. That's also worth working on as well. Okay?